Here's an example problem that's commonly done in intro physics labs, where you have a cart moving horizontally on a track, and it's connected by a string that goes over a pulley to a hanging mass. So this is often called the half Atwood machine because of the similarity to the Atwood machine, where two masses are hanging over a single pulley. So in this problem, we have the two interacting objects. We want to know what is the acceleration and what is the tension in the rope. Now, before we even start drawing our free body diagram, it's important to define our axes. So I will go ahead and make the positive x-axis to the right and the positive y-axis point upward. Okay. So the first thing that we want to do is pick one of our masses that we're going to draw our free body diagram for first. So let's go ahead and do mass 1, the hanging mass. So we're going to have a downward force of gravity and an upward force of tension. And that's it. And we can write our Newton's second law equation. So we can say F net 1. Now this is only in the y direction. There are no forces in the horizontal direction. So making sure that we remember up is positive, so we can say that's going to be the force of tension minus the force of gravity is going to be equal to mass 1 times acceleration. Now, we should be careful here to let's label that acceleration 1, and really should label this F sub g1 because there's going to be a different force of gravity on the other object. Now, a lot of times I even like to skip the step of writing F sub g because I know that I can always calculate this directly, and it's just going to be m1 times g. And that, using that just makes my calculation, or my notation a little bit cleaner. Okay, so that's an acceleration, or sorry. Okay, so that's an equation that I can use that I got from looking at the free body diagram of mass 1. Now let's look at the free body diagram for mass 2. So mass 2 was the cart. And we've got a force of gravity, I'll call it F sub g2, pointing down. We've got a normal force, I can just call that F sub n, it's the only normal force in the problem. And then there is a force of tension pointing to the right. Now you'll notice that I already labeled the force of tension as being the same in both of these cases. And that's because I know that it's the same string, so the magnitude of the force of tension is going to be the same in both cases. So now doing the net force equations for this mass, I'm going to do the y. So I'll call it F net 2 in the y direction. It's a lot of subscripts, but I'll do the y first because this is not really going to be anything all that useful. And so this is going to be equal to the mass of the object times the acceleration in the y direction. But I know that the cart is not accelerating in the y direction, so that's going to be equal to 0. So the reason why I said that this is true, this is a true equation, but it's not all that useful, is all this tells me is that the normal force balances out the force of gravity. I'm not going to do anything with that. Now, if I had a problem where there was friction involved, here we're ignoring friction, then I would have to calculate the normal force so that I could later calculate the force of friction. Okay. So in this case, it's not useful. Okay, and then the net force equation in the x direction is really simple. It's the force of tension is equal to, well, that's the only force in the x direction, so that's going to be equal to ma for that object. Now, it's important to remember that's mass 2 and also acceleration 2. Okay, so let's copy the equations that are going to be actually useful. Now, the first question that I have here is how many unknowns do I have? I've got the force of tension, that's 1. I've got acceleration 1, and I've got acceleration 2. So that's 3 unknowns, and I only have 2 equations. So I better figure out some other information or else I'm not going to be able to solve these. So the question is, how does A1 compare to A2? So because the cart and the hanging mass are tied together, the magnitude of the acceleration is going to be the same for both. Right? When the cart moves 1 centimeter, the hanging mass also moves 1 centimeter. So their velocity magnitudes are always the same and their acceleration magnitudes are always the same. But the question is, are they both positive or is one the negative of the other? So if I go back to my picture, I can see that if the cart moves to the right, that's the positive x direction. But when that happens, the hanging mass is going to move down, and that's the negative y direction. So that means that A2 is equal to the negative of A1. Okay, so that means that A1 is equal to negative A2. Right, and I'm going to use the acceleration of the hanging mass as the negative one because I know that if I just release these from rest, the cart's going to move to the right and the block is going to move down. Okay, so with that, I can simply rewrite these equations with, and I'll just call it A now instead of A1 or A2. So I'll put a minus sign there, and then I've got the force of tension here is equal to m2 times the acceleration. So at this point, all the physics is done. You've done your free body diagrams, you've used Newton's second law, you've got two equations that relate the two unknowns. And so at this point, the rest of the solution is just algebra. Okay, but sometimes that algebra can be a little tricky, and we have two equations with two unknowns. So my general strategy is I always try and solve both of the equations for the same variable and then set them equal to each other. Sometimes there's something that you don't know but also don't care about. Right? A lot of times you don't actually care about what the tension in the string is. In this problem, I wanted to solve everything just so that I could demonstrate everything. So in that case, you would solve for the variable that you don't know and don't care about. But in this case, we can pick either one. I can notice that one of my equations is already solved for F2, so I will solve this other one for Ft. So I'll add m1g to both sides. And that's going to give me Ft is equal to m1g minus m1a. And then Ft is also equal to m2a, so I can set both of those sides equal to each other. So setting those expressions equal to each other, I get m1g minus m1a is equal to m2a. And I want to solve this expression for a, so I will add, I want to get all the terms with a on the same side, so I'll add m1a to both sides. And that gives me m1g is equal to m1a plus m2a. Then I can factor out a times m1 plus m2 is equal to mg. And then I want to get acceleration by itself. So I divide both sides by m1 plus m2. And that gives me that the acceleration is equal to m1g divided by m1 plus m2. Okay, so that's a general expression. That would be true for any combination of masses. But if I want to get the number based on the numbers that were given, the acceleration is, well, I'm going to have, let me put the g out in front. So I've got m1 was 0.5 kilograms. And then m2 is 1 kilogram. So 0.5 divided by 1.5 is 1/3. So the acceleration is going to be equal to 1/3 of g, which is 3.27 meters per second squared. And then I also wanted to solve for the tension. So now I can go back and copy an equation that I had, which was that Ft was equal to m2a. And so now I know the acceleration. M2 is 1.0 kilograms times the acceleration, which is 3.27 meters per second squared. So that's going to give me 3.27 newtons, which both of these should really be two significant figures. So 3.3 newtons would be the tension. A common pitfall or mistake that I see people make with these type of problems is what I call jumping to conclusions about what's at the other end of the rope. Right? So they see that there's a force of tension this way, and they say, well, what's on the other end of the rope? There's a hanging mass. So they say, well, Ft must be equal to the force of gravity on that mass, right? And the answer is no. If we look back at our solution, we found that the force of tension was about 3.3 newtons, and the force of gravity on the hanging mass is 4.9 newtons, right? Half a kilogram times g. So you really can't try and guess what's going on there. Now, the other way that we can know that that's not going to be the case is that force of tension has to be the same as this force of tension, right? Because it's the same string. Well, this force of tension can't be equal to m1g, because if that were the case, then this block, the forces on it would be balanced, and it wouldn't go anywhere. Right? So we know just by the fact that the acceleration is down, that means that m1g must be bigger than the force of tension. Okay, so if we take a step back and look at that, we can think, okay, it can't be just equal to m1g, the force of tension. But doing the free body diagrams and setting up the equations that way is really designed to protect against jumping to conclusions like that. So that's why when you draw a free body diagram, you only look at that object. Then you write down the Newton's second law equations for each object and each direction separately. And then when you've got all that written down, then you can say, okay, what might be in common between them? I could say, okay, it's the same rope, so the tension's the same. They're tied together, so how is the acceleration related, like we did earlier in the problem? So it's important to keep that in mind because it's something that it's a very common mistake that people make. So now another interesting observation, if we go back and take a look at this expression here and copy that over, we can say, well, this is if we treated the block and the cart as a single system, we could say that this is the net external force. Because that's the only unbalanced force on the system as a whole. The normal force and the gravitational force on the cart balance each other out, and the tension is internal to the system. So then that net external force should be equal to the acceleration of the system times the total mass of the system. Right? So that's the mass of the system and times the acceleration. That's really, you can think of it as Newton's second law for treating the whole system as a single object. So that's kind of a way that if you kind of visualize or see that, it's a way to kind of jump past some of the algebra. But if you wanted to know the tension, which is an internal force to that system, you wouldn't be able to do it by looking at the problem that way.
Now you must acquire a taste for freeform jazz.